In this video, I want to look at what happens to the R-squared measurement of a fit when we set the intercept, the constant, to 0. Okay. Now, there are times physically that you want to do this, that you have a theory, say maybe Hubble's law, you have velocities and distances of objects from some point, say the Earth, and velocities that they're moving away from the Earth, and the theory, the simple theory here suggests that has no constant. Or similarly in Ohm's law, you have voltages and currents, and the simple Ohm's law has no constant, no intercept. So there are reasons where the theory suggests that maybe you don't want a constant. And then sometimes I was working with this just this data of crickets, how fast they chirp based on as a function of temperature. And so I had that data here and plotted it. And then I brought up the regression. So here was the regression with a constant and was looking at the p-values. And the p-value for the intercept was large. So I thought, what would happen if I set it to 0? To that sort of, the p-value, the null hypothesis would be that there is no intercept. So what would it look like with no intercept? And then one of the things I was plotting on my graph was R-squared, and I expected R-squared. People often tell you R-squared tells you the sort of the percentage of the values explained by the prediction. And so if you take away the constant, you're taking away some of the flexibility of the fit. And so I expected R-squared to go down, but it went up. And so that confused me. And so then I had to do some digging. Okay, so that's where this all arose. Okay, so I plotted this cricket data. I did a regression. The p-squared of the constant was high, suggesting maybe I didn't need it. But if I set it to 0, R-squared did not what I expected it to do. Okay. So there are sort of two ways in a usual linear fit. There are sort of two ways to calculate R-squared. And I'm showing them both here. You're producing this 0.69229, which is what I was getting for the R-squared here in my fit. And so one is based on a prediction. I'm making a prediction. I'm proposing a slope and an intercept. I'm making a prediction. I am calculating the residual, the residue, the difference between the prediction and the value, and adding them all up. And so that is, and one approach of R-squared involves that. So there was that prediction and residue and summing them up. And here's a formula that involves that E4. The other one is I-19, which I will get to. Then there is a formula that you get the average of your X values, the average of your Y values. You get these sort of, I'll call them deviations, square deviations, deviations for Y, square deviations, and X deviations times Y deviations, and you sum them up. That's these gray things here. And then you can use J and G and I, and these things all what can I say, are dependent on the data and not on the prediction. So hitting there are these two ways to get R squared, and one of them has sort of nothing to do with the prediction whatsoever. At least, and then this one that clearly does involve the prediction. So, okay. Then, as I said, I set in Excel, it allows you to set the constant to 0. In fact, it allows you to set the constant to anything. And so here is the plot with the constant set to 0 and the R squared is going up. I redid the regression in there, and so this is the original regression. Here's the regression with no intercept. So, and here we have the R squared, and then there are these different values here. Okay. So that is the mystery I was trying to solve. Why did R squared go up? Was it just some weird Excel problem? So then I brought in R, and I brought in this library, and to allow R to give me R squared, and I do a similar thing here. I'm doing it in R. I can make a constant. So there is my fit. What I'm calling my fit 2 is a regular linear model, but my fit was a linear model with the intercept set to 0. And then we see, similarly to what we saw in Excel, there's an R squared of 0.9969, 0.997 here in Excel. So R is agreeing with Excel. So whatever Excel is doing, R is doing. And then I looked over at Wolfram Cloud and did the same, brought in the data, made a list plot, did a linear model fit, and then a linear model fit in which I set the constant to 0, include constant basis false, and got for these two fits, Cricket Fit 1 and Cricket Fit 2, I found their R squared, and it was also agreeing. So whatever Excel is doing, R is doing, and Mathematica, Wolfram Cloud, is also doing. And I went over to Python, but it's not the same in that here I used matplotlib and numpy, and then also brought in to get me this R2 underscore score to bring in this something to calculate the R squared. So I was bringing in these libraries and made the same plot and did the fit. And here is the fit, setting this degree 1 here in NP polynomial. And I'll make all these files available in a link in the comments in case anybody wants to look more closely at them. But this set the constant to 0. And then I'm sending it off to R squared. But the way this R2 score worked is that you are sending it the data and the predicted values. And so therefore, it is using this formula, the one based on predictions, And so uh, then it has the behavior that I expected, that uh, r squared would be close, but it would go down. It wouldn't explain quite as much of the data because it was not the best fit. It was a slight, somewhat not as good a fit. So in my original expectations, the Python approach was doing what I expected, but Excel and R and Mathematica were all doing something, and then the question was, what are they doing? And then that question poked around, and that was finally answered here by this stats stackexchange.com, that there is when the constant is set to 0, they change the formula. So the r squared formula changes, and uh, and then here's another sort of paper on it, sort of giving more explanation. But they have some statistical reasons for, if there's no constant, I'm going to use a completely different formula, and that is what happened. So they changed this formula. So then I came back here to the original uh, approach and said they do y prediction minus y average and just the y squareds, and then this this sum of the y squareds is, so we're making this comparison here of, this was based on the prediction, this was the formula based on the predictions, and it's divided by I-19, which is this y minus y average squared. Whereas over here, the one that matches up with the constant is the y minus y average is just replaced by y squared. And so, and that's the change in the formula, that's the difference. And we saw uh, here that is what Excel does, so without telling you. This is what R does without telling you. This is what Mathematica Wolfram does, sort of again without telling you. But so that explained for me this mystery, that there was a change in the formula. So my expectations of what r squared would do as I changed the number of parameters sort of made sense. Then I had this sort of here just to tell you that what I was originally thinking was not nonsensical. I did sort of a plot with the normal linear constant, slope and constant, and a fit to a polynomial of order 2, a quadratic. And we see here that there are more fitting parameters, so it incorporates the linear and has more, and so the r squared goes up. And then there are things called adjusted r squared to figure out, are you overfitting or not. But this was my expectation, that with more fitting parameters, I am course fitting better, explaining more of the data, and r squared should go up. That's why I expected my r squared, when I took away the constant, to go down, but it did not, because there is a switch in the formula. And then one last thing I want to show you here is that, again, there are these two versions of r squared that can be used for a linear fit. And one of them has no notion of the fit whatsoever. It just is all about the X's and the Y's, just about the data. And I want to just do a little funny playing here. So one way I was trying to go about this to sort of to trick Excel into getting what I wanted was there you can not only set the intercept, but you can set it to whatever you want rather than just 0. And so I was trying to set it to something small, but not 0. And it was sticking to this 0.6923. And that seemed, I wanted it to get to this other value of my, I wanted it to go down from there, and it wasn't going down from there. And let me just make it extreme here. Let me put in a crazy value like 50. And so now we have this not fitting the data at all, going the wrong way. But it still has the R squared of 0.6923, even though it's clearly a much worse fit than it had been. And that just suggests to me that Excel is using this R squared that's based just on the data and not on the fit. So I had two formulas that produce the same thing if I'm doing just normal linear regression, but one involved just the X's and the Y's, the other one and explicitly involved the prediction. And here I've made just a terrible prediction, and the R squared hasn't budged. So they must be using this one that just works with the data. Okay, so that's what I wanted to show. And again, when it's, if I make it 0.0001, it's giving me R squared of 0.692. If I'm doing, if I change it to exactly 0, then it jumps to this 0.997 because it's at 0. If it is 0, it is changing the formula. All right, it was just a mystery to me why the R squared went up instead of down when I set the constant to 0. It's because there is a change in the formula. The calculation's not that difficult. If you want to do the calculation like in Python or, in R or Mathematica, you can sort of do it yourself. But if you're just relying on them, then they switch formulas for the constant being 0. That's all for this one. Thanks for your attention.